Slides should be up.
Yep. Okay, looks like we're rolling and we're also recording. So welcome everyone to this Wednesday with Wing webinar in June. And this is, it's a very sunny June, and we're very happy to have Trystan with us, who I will introduce shortly. But before that, a few housekeeping rules as usual. During this webinar, I think all of our attendees, or everyone here, you'll notice that you're on mute and your cameras are off. Once we get to the Q&A section of this webinar, we'll enable people to unmute themselves and turn their cameras on, just to encourage a nice discussion at the end. Yep, and Trystan is also very happy to take questions. Also, if you want to get questions down during the actual presentation, you can put them in the Q&A section, and if there's anything wrong with that, just please put it in the chat instead. Yes, I think that's all for our housekeeping. Without further ado, I will introduce our speaker today. That's Trystan Cowan, and he is a geologist in the Energy Geotechnics team at Arup, with over 4 years of experience in geothermal, underground hydrogen storage, and CCUS infrastructure, applying petroleum systems backgrounds to feasibility studies, concept design, and subsurface risk assessment. So a wealth of experience, and yeah, no interest in from working with him at Arup as well. Over to you.
Thank you, Simran, and welcome to everyone. Thank you for inviting me along today to present to the Wing Network. It's an honour to be here and lovely to see you all. And yeah, it is very hot today. I'm currently based on site and luckily managed to secure a portable AC unit. So yeah, I won't hopefully be sweating too much at this presentation. So today I'm going to present to you on geothermal enabled carbon capture and storage, and trying to address the main question, that is, how can geothermal heat address the energy challenges of CO2 regasification? So, little overview of the presentation. So, I'm going to give a quick introduction to myself, Arup, and geothermal at Arup. And then for those of you that might be new to the sector or studying and looking to explore that as a potential career opportunity, we'll have a quick geothermal refresher on technologies, drilling, the market, and current policy context. Then we'll get into the meat of it with a case study on Morecambe Net Zero. And this is where we'll look at geothermal enabled CCS, the challenges and the approach we took, the implications and why it matters, and then a little look into how we could deploy that in the UK and where there are potential other opportunities. So quick introductions to myself. So I'm from Aberdeen originally. I'll be supporting Scotland in the World Cup tonight. Hopefully we can get out with the group stages for the first time. I went to the University of Edinburgh, where I studied geology and graduated with a master's in 2021. Did my master's thesis on geochemical reactivity of hydrogen in depleted gas reservoirs, which has since been published. So I've always had an interest in the energy sector and geoenergy from my background growing up in Aberdeen with the extensive oil and gas sector. And then with my interest in kind of making a better world and helping future generations enjoy the same livelihood that I have, I wanted to go into that renewable side rather than the oil and gas. So then back in 2022, I joined Arup, the geoenvironmental team in Sheffield, but with my interest always lying in energy, I was quickly taking up any opportunity that I could to get into geothermal or applied geology within the energy space and underground gas storage from my thesis experience. Following that, I pushed for a transfer down into the Energy Geotechnics team in London and have been down here since the end of 2025. Key areas I work across now will focus on applied geology, risk assessments, geothermal, and as I mentioned, underground gas storage. So some of my project highlights from my time at Arup so far. is the Woodsmith Deep Gas Risk Assessment. Some of you may know the Woodsmith polyhalite mine, which is a 1,600-meter mine and with a 37-kilometer export shaft, well, tunnel that goes all the way to Whitby from the mine head that's 37 kilometers long. And we conducted a risk assessment on that, which is really interesting. And then the Spirit Morecambe Net Zero geothermal assessment that I'm going to discuss in the case study today. And then we have also recently been doing the Peak Cluster CO2 pipeline hazard assessment, which is the source of the CO2 that is being put into the Morecambe Net Zero field. So it's really nice to have that full product cycle and CO2 cycle experience and seeing that project come from the source to the sink where the CO2 will be stored. So a quick one about Arup. So Arup is a global collective of designers, consultants and experts who are dedicated to sustainable development and to using imagination, technology and rigor to help shape a better world. We were founded in 1946. We have about 17,000 people globally and 6,000 of which sit within the UK. We've been turning over about 2.2 billion a year for the last few years and have 100 offices and in over 35 countries. One of the great things is being able to work in any of those offices for a month every year. And I made the most of that by working in the Melbourne office for a few weeks at the start of this year. So then quickly about what we do within the geothermal team here at Arup. So our geothermal team delivers shallow and deep geothermal projects across all aspects globally. This ranges from shallow and deep to national ground source heat pump and geothermal mapping projects. This is across resource characterization and feasibility studies, as well as planning, permitting, policy support. We also do transaction advice, which is some of the more interesting stuff. We work with our business investment advisory team. We have recently advised on a very large due diligence project for a sale of a geothermal power plant in Turkey. And we do work a lot across internal and external teams, and we can deliver projects locally within Arup from inception to delivery of that final business case and design. So a quick geothermal refresher for those that might not have worked in this space recently or are new to this field. So within geothermal, really, we have two broad categories of wells or systems. So we have shallow geothermal, which typically is less than 500 meters and consists of ambient temperature that can be used for heating and cooling. This can range from open to closed loop, and that is shown on the left of our figure. We have depth down the y-axis of the figure and different aquifer and coal measures and target horizons in there as well. These are the typical temperatures that we can also see at those anticipated depths. So closed loop vertical wells, open loop wells and mine systems are typical shallow systems that may be deployed. And then there are also standing column coaxial wells, but these can be put across deep or shallow systems. And then to the right of the figure there, we have our deep geothermal systems, and these typically exceed 500 meters, but are often up to kilometers in depth to achieve the required energy levels and temperatures that they need for the large heat off-takers. Some of the new emerging technologies that aren't shown on here are deep closed loop advanced geothermal, as well as oil and gas conversions. These are currently being looked at in Canada and Texas. There's a company, Seraphy, that are exploring that in the UK. Additionally, there can be a hybrid shallow or deep system is underground thermal energy storage. These are typically low technological readiness levels and haven't been deployed at scale as of yet. So another key difference that I briefly mentioned there is the difference between closed and open loop geothermal systems. So closed loop can effectively be installed anywhere, and because they just contain a closed environment, as is in the title, where fluid does not exchange with the ground. The fluid is retained within the well structure and the heat is transferred through the walls of the well and into the thermal fluid. Whereas open loop, this can only be deployed in specific locations where there's sufficient flow, temperature, and porosity permeability. And that is where you'll have the exchange from a withdrawal well and a reinjection well. So you'll withdraw the hot thermally charged fluid, send it through your heat pump or your system, your heat exchange system, and then re-inject that back into the aquifer where you withdrew it. So that's a quick summary, and now we'll go on to the context of geothermal within the UK. So currently geothermal is a pretty hot topic within the UK, and that's mainly being driven by our Minister, Lord Whitehead, and the recent release and development of some key projects within the UK. So yeah, as I mentioned, we have a geothermal minister now who's designated to promoting geothermal within Parliament. That is Lord Whitehead. And we've also recently had some major projects delivered, such as the heat network zoning and the new geothermal platform by the BGS, which is a great resource for anyone looking to explore geothermal potential and research or conduct delivery of projects. So there's also GeoMap from Project Innerspace, which is a large American investment and has looked at the policy landscape. We've also had our first cost model for the production of geothermal heat and power, which was published by Arup back last year. And that has been a large piece that has really set the framing for the cost potential and where we could reduce that in the future. Some key projects have also come online recently, such as the United Downs, which you may have seen in the news, which has generated its first electricity. And there are other major projects such as Gateshead, the coal geothermal, and then Lancashire Wines, UK Geos, Southampton, various hospitals and universities that are all looking at deploying geothermal where they have those large heat off-takers and demands. Some of the key barriers that still remain are communication. So it's great that we're hosting these kind of events where we're publicizing and promoting geothermal. It's a great thing that Wing does, bringing this into the light of public and publicizing it further. So yeah, unfortunately, public understanding of geothermal technologies and deployment opportunities still remains low. Additionally, the support mechanisms from the government are lacking, and we've recently exhausted and the previous funding mechanism has expired. So yeah, hopefully we can get some more support down the line from maybe one of the contracts for difference be included in there, where it'll be have a strike price and then auctioned off to developers. But I think we may be a little bit behind and we still need that high capital investment. So where do those opportunities lie? So within the UK, geothermal is typically behind the US and the European neighbours and markets. However, that means we do have the opportunity to learn from them and hopefully increase the deployment of geothermal technologies rapidly. For example, two projects in the US have recently delivered a step change in geothermal economics. This from a company called Fervo, and the Forge project, which in 2025 drilled a well to 4,800 meters, producing bottom hole temperatures of 270 degrees, and they completed that in just 16 days. This would typically take around 3 months within the UK, and that produces a 5 times increase in the drilling speed. One of the great things we do have in the UK is an extensive experience of drilling from the North Sea oil and gas industry, and hopefully some of those skills can be industries and people can be reskilled into the geothermal space. If we can recreate those kind of drilling rates over in the UK, then it could revolutionize the economics of geothermal and help projects and wells be installed far more quickly. The key technology differentiator that Fervo brought in is the diamond drill bits, which, as they do come at an extra cost, the reduced duration of drilling pays back that cost very quickly. Further opportunities that we see, so now looking at some of those little images on the right, is as I mentioned, the National Zoning Model project. So this can hopefully help the UK and heat networks to streamline their approaches. these technologies have been deployed across the UK and Europe. Well, have been deployed across Europe readily, and we're hoping to deploy them across the UK, where you have specific heat networks within cities where geothermal energy is connected to heat users such as offices, industries, and homes within built up areas. And given the current heat wave, it is also important to consider opportunities for cooling and rejecting heat back into the ground, which can then be used during winter months. And this is the basic principle of underground thermal energy storage, or UTES. So another opportunity we have is the deployment at hospitals and airports, as I mentioned earlier. And there's some big projects. There's 8 hospitals still currently exploring geothermal, and York University is installing a system currently. So one other key thing in what I'll be discussing today is the use of supporting and enabling carbon capture and storage. So in the recently published 7th carbon budget, draft legislation put forward that we're going to require an 87% reduction in emissions relative to the 1990 levels by 2042. And this is going to require a reduction of 260 megatons per annum if we're going to achieve this. And I know that sounds like a really large amount. It's very hard to quantify, but the project that I'm going to talk to you about later, the Morecambe Net Zero project, is looking at potentially storing, I think it's 3 megatons per annum. Well, that's what they're capturing from the peak cluster, but I think they're looking at storing 25 megatons per annum at peak capacity. So yeah, with the rest of the CCS projects across the UK, hopefully they can get forward and up and running, then we should have a chance at achieving those numbers. So generally, the UK is at the start of its geothermal journey, and there's growing evidence and momentum building, and this will hopefully increase. I hope you're as enthusiastic about this topic as I am. Sure you are, otherwise you wouldn't be on this call right now. But yeah, please promote this, tell your friends about it, share it on LinkedIn, as that's one of the best ways we can grow awareness of the sector and hopefully build and promote it further. So on to the next one. So I'm going to now talk about the case study. So yeah, as I mentioned, we're going to discuss Morecambe Net Zero. So a quick project overview. So Morecambe Net Zero, as you can see on the figure on the right, I don't know if you can see my mouse, or I have to put it on the main screen. I think the main screen works. Yeah, so as you can see from the little inset figure here, we're based over in the centre west of the UK. And this is near the Peak District and into the Morecambe Bay and around the Wirral by Liverpool, Blackpool and Morecambe. So the whole project is looking at combining capturing CO2 from the Peak District and then transporting that out to the Wirral in Liverpool. This is going to be transported by a shallow buried pipeline and then sent offshore into the East Irish Sea and stored in Morecambe Bay in the north and south Morecambe gas fields. These gas fields have been recently depleted, and yeah, as I mentioned, that plant capture of CO2 from this cement works is one source of CO2, which plans on capturing 3 megatons per annum, but they're also going to be looking at bringing in liquefied CO2 from ships and also piping any additional CO2 captured from the HyNet cluster in Liverpool out to Morecambe Net Zero if the capacity is exceeded, as that is a smaller CCS project. From the Wirral, it's a 25-kilometre move out into the East Irish Sea. And luckily, Morecambe Net Zero have, well, not luckily, through a lot of time and due diligence, they've been granted their storage application license in 2023, and that is now going into the next stage of consideration. So what is the process flow for capturing CO2 and storing it underground? So the figure on the top there shows you the transition from the capture and then sent into the pipeline. And that pipeline can run all the way to the CO2 conditioning plant, or alternative routes for transport, as I mentioned, is through shuttle tankers through liquefied CO2, where it has to go through a buffered storage process. So there are different options there for CO2 transport, and those, of course, have different energy demands. The CO2 injection is planning on starting in 2030 and ramping up to 25 megatons per annum by 2040. And combined between the two fields, they could store up to 1 gigaton of CO2, which would be 4 years of that annual storage requirement to reach our 2042 target. So there we go. So that's what the project process is. And one of the key constraints of the project is the high energy requirement associated with transporting and storing and then regasifying liquefied CO2. And this is where the geothermal element comes in, and we can look at using that as a potential solution. So a little deeper dive into the site layout and setting the context of why we need or may need geothermal to support this project. So at stage 1 on the figure on the right there, this is the first stage of the import of liquefied CO2. You can see the map here showing the port of Barrow, where you have the main jetty there, and then the proposed CO2 plant here for the Spirit Energy site. And the first stage is importing that liquefied CO2 from the ships at the port jetty, and that CO2 is coming off the boats at -30 degrees. That is then sent to the ambient temperature processing facility, where it's held in the buffer storage at stage 2. And that is going to bring it up to 0 degrees. We did consider using thermal energy from the salt water, well, the sea. So yeah, water storage, but the energy, the cool that it would have let off would have exceeded the requirements and planning conditions, as it's quite a sensitive environment in a triple SI. So then after stage 2, it gets sent across to the regasification process facility, where it needs to be increased up to temperatures around 40 degrees centigrade before it is sent into the offshore transport system and, yeah, put underground. So that requires a massive energy change. We have a delta T, or a difference in temperature, of 70 degrees, and that could require an estimated 40 to 120 megawatts of power to provide that heat. And that was determined from the mechanical and electrical and process engineering team that was doing a concept study on this project at the same time as we were. So they were doing the main concept study, and then we identified this bottleneck, and we as the geothermal team were brought in to try and see if geothermal could offer a suitable solution. So that is the main context of the problem, and now we'll go into the ask and the why. So Spirit Energy came to us and asked us whether we could look into geothermal heating and heat pump technologies, including ground source heat pump systems, closed and open loop, surface water heat pumps, sea source, and deep geothermal coaxial and hydrothermal doublets. This study was an initial feasibility study, an optioneering exercise to help inform investigations and prioritize technology selection. I must caveat and say it was not a detailed assessment and relied upon published and available data sets. No site works were undertaken as part of this work, and so that was recommended as next steps. So a background on the project itself. So as with all good studies, one of the main stages, and this first stage is always a deep dive into the data and to develop a conceptual model. So to inform our work, we reviewed 4 deep wells that were local to the site, as you can see on the figure on the right there. We have the Morecambe Net Zero facility here, and these 4 main wells that were accessed on the BGS GeoIndex and UK Onshore Geophysics Library. And then we also looked at 3 offshore wells, which were our best indicator and analog for one of the target horizons, which was the Sherwood Sandstone group. And we used the North Sea Transition Authority data sets there to review the logs and well reports and indicate and inform our porosity and permeability in the ground model. We also extensively reviewed the BGS maps, the regional maps, and seismic lines from the UK Onshore Geophysics Library, as well as the UK 3D dataset. Fortunately for us on this project, it was a really good learning opportunity, as we were working with Spirit Energy, who are an oil and gas developer originally. So the client had extensive knowledge and data sets from operating their North and South Morecambe fields that were just offshore. As you can see here, where their main site is and the inset is, their fields are about, as you saw earlier, 25 kilometers offshore. This meant that we had extensive access to cores, flow tests, petrophysical reports, which were very useful in constraining the modeling parameters for our 1D geothermal models. This is the first time that we've worked with the developer with this much data, and it really helped us refine the data and the models and improve our reliability. So, as a geologist, and if any else of you are here in the call, we all love a good map. So here it is. This is the geological setting. As you can see on that figure on the right here, and then the small inset at the bottom right of that, the little red blob indicates the site, and that is that we're located between 2 major faults. So on the east of the site, we have the Yarslide fault, and then on the west of the site, we have the Lake District boundary fault. So in the bigger image, you can see the line of section there, and then also on the smaller image, the line of section from one of the BGS cross sections on their regional maps. Fortunately, ran just to the south of our site, so we could rely on that as a good source of information for interpreting our ground model. And then on the left there, you can see our cross section with the site labeled at the top. The Yarslide fault was to the east of our section, and the major Lake District boundary fault that is downthrown to the west on the left of our site, on the west of our site. So we split the site up into 2 key ground models. We have the east fault block to the east of the fault, and as you can imagine, the west fault block to the west. And as you can see here, the Sherwood Sandstone, which is this dotted peach color, is much shallower in that east fault block and is downthrown across to the west, which is what we identified as one of our key target horizons. As you can see, there's a little bulge there on the top of the cross section, and that is representative of the little spit here where the bigger one well is, just for reference. So now we know what's input into the 2 ground models. I'm going to show you the temperature profiles that we developed for the project. So we developed key ground models for each of those east and west fault blocks. And as you can see on the east, we have a thin superficial layer that overlies the Sherwood Sandstone bedrock and a Silurian deposits at depth. And then below that, again, the Carboniferous. And then on the west fault block, you can see it's all downthrown slightly further with an offset of a few hundred meters. So when we were generating our geothermal gradients, we used the Busby et al. Paper from 2011, as there were no direct temperature measurements from any boreholes that were close to the site. And from that, we inferred geothermal temperature gradients between 19 and 23 degrees. And if we take those range of values with a surface temperature of 11 degrees, we could assume that at depth of 1 kilometer, we may have 34 degrees temperature. So looking at the 2 fault blocks, we identified the west fault block as the most preferential target. And we looked into that most earnest, and as you can see, the Sherwood Sandstone, which as we know across the UK is a highly productive aquifer, and that is also the aquifer or reservoir in their case that they were producing from in the South Morecambe fields. So they had a wealth of data from that, and it was great for constraining our model. As you can see, the black dots on this, we have the, as I should have mentioned, we have the depth on the y-axis and temperature along the x-axis. We have our geothermal gradients with the upper and lower bounds plotted going across the graph there. And we have a BGS temperature measurement that aligns within our zone of interpretation at depth, which is great for validating our inferred temperatures. So moving on to what the outputs were. So this geothermal data was used to input into our geothermal modeling. So what did we do for the modeling? I know there's a lot of information on this slide, so I'll take my time to set it out clearly. So we developed 1D reservoir models using Doublet Calc, which is a TNO software. And on the left there, we have the reservoir data and geotechnical input parameters that we derived from our ground model. And on the right, we have the probabilistic heat capacity estimates and the main outputs in thermal power. On the left, we have different inputs here. So I'll talk through a couple of the key ones. So the top producer, so the bottom of the aquifer where we are producing the thermally charged fluid, was at around 2,400 meters, and we estimated a bottom hole temperature of 60 degrees. And with production of that, we could take around 25 degrees centigrade of thermal energy out of that system. This model that I'm presenting here is for the Dinantian limestone, so the deeper target horizon in the East fault block. And as I mentioned, the East fault block was the less preferential, but this is the deepest target within that. Because of the limestone, we estimated a lower permeability, and from BGS data and the regional reports. And yes, so we have a medium permeability of 200 millidarcies. It's important when we then compare it to the Sherwood sandstone, which is our primary target. And yeah, you'll see how high those thermal output, the flow rate jumps. So going back to the graph on the right, we have probability up the y-axis with 100% probability or likelihood of achieving those energy values or thermal power at the top, so 100%, and then 0 at the bottom. And then along the x-axis, we have thermal power in megawatts thermal. It's important not to confuse this with raw power or electrical power, which would be megawatts per hour or megajoules. So on the graph here, we have the outputs. So we have the P90, so 90% chance of achieving around 3 megawatts of thermal energy. We have then 50% chance or likelihood of achieving around 4 megawatts, and then 10% likelihood of 6 megawatts. When we are using these values to inform our estimates of cost and assess risk, we always use and recommend using the 90% to 50% probability range to improve the certainty of obtaining those values. So now I'll show you what the potential outputs are for the Sherwood sandstone in the deeper West fault block. So again, on the left, we've got our geotechnical inputs, and as you can see here, because of the shallower depth of our target horizon at 1,200 meters, we have a lower bottom hole temperature of 41 degrees, and we can therefore take less of that thermal energy out. So our delta T is only 18 degrees. But if you look at the aquifer permeability, and this was taken from core logs and validated by Spirit Energy, because we were quite shocked when we saw the level of maximum permeability at over Darcy level flow, nearly 1.5 Darcys. But yeah, they said from their experience with producing from the reservoirs in the Sherwood sandstone group, it does regularly achieve over Darcy level flow. So even though, because of the extensive data we had, we used that median value of 370 millidarcies to inform and input into our power estimates. So the probabilistic heat capacity estimate that we can attain from the highly productive Sherwood Sandstone aquifer is at that P90, so 90% likelihood, is nearly 5 megawatts, which is a significant increase from the 2 megawatts in the deep, albeit deeper, but Denantian limestone in the east fault block. So, yeah, down at P50, there's nearly 8 megawatts, and at the very high end, so say you achieve the maximum or near maximum flow rates and near maximum temperature, you could potentially generate 14 megawatts of that thermal energy from one well doublet. So yeah, it's important to stress this is for one deep open loop well doublet. There is one injector and one withdrawal and one reinjection well. So a key thing just to set this in context of where the energy requirements are for the general project. So with an estimated heat demand of 40 to 120 megawatts, if we took the midpoint of that at 80 megawatts and the P90, which is the most likely, well, nearly the most likely potential of generating that amount of thermal power of 5 megawatts, if we put in 8 well doublets, which is possible at their site because they have access to so much land, we could generate nearly 40 megawatts of thermal energy, which could reduce their heating power demand by nearly 50%. And this would have significant impact on the project and reduce the costs and improve long-term energy security. So, additional benefits to the site are there are a lot of other heat users around the area, and because it's a low temperature demand heating process, so the rate of temperature that's input requirement is just the high volume and mass of material that needs to be heated in that liquefied CO2, there's potential for supplying. We don't need those super high temperatures that you might see from like volcanic zones or other highly hot regions across the world, and also the temperatures you'd need from district heat networks. So kind of key next steps that we'll look at and I'll discuss a bit further is drilling those wells to explore the site and prove our assumptions, and looking at the different targets between the Sherwood Sandstone and the carbonates, and also whether the fault would produce any increased flow rates, and that could be targeted as well. This will help us refine our assumptions and also lead to acquiring new geophysics and, yeah, further refining our models. So on the next slide, so this one is where we started to take a look at the cost implications for the different technologies. So this is a really great figure produced by Spirit Energy themselves. Their data, we've been working closely with them since delivering the project and promoting geothermal and this project itself. So yeah, Phil Ware from there produced this figure. And we've got, as I said, thermal power and megawatts thermal along the x-axis, and then the cost per millions up the y-axis. And I will caveat here that this is the front-end loading level 1 cost, which is plus 50% on the cost. So the very highest level estimate that you can apply because of the early stage of the feasibility and concept design. So we can see here that the different colors of the icons present the risk of that technology. So we have high, medium, and low risk. And then the pink blobs and lozenges around those technologies are the power estimates of them. And I will caveat here that they have used the 50 to 10% likelihood, so the least likely range, so from 10% likelihood to 50% likelihood for these. So it is the upper expectations, but still we can see that for a 1.2 kilometer deep well doublet, which even though it will cost around £50 million to deploy, could generate between 8 and 16 or 8 and 14 megawatts thermal power, more likely between that 5 and 8 megawatt thermal range. So what does that show? we have the lower end technologies here. So your safe loop, shallow water heat pumps that are your moderate capacity, low cost. And then you have your closed loop, which are very low risk because you don't have to rely on the ground conditions and permeability of the rock, but you would have to include around 385 of those systems, which even at that rate would cost a lot less than just one deep well, which is interesting. But yeah, you don't quite reach those kind of upper powered levels that you could from deploying multiple deep well doublets. So yeah, and realistically, the deep geothermal has the highest uncertainty, and cost, but that relative risk and then production and Given Spirit is much better. So Given Spirit Energy's appetite for risk, being an oil and gas developer and being comfortable with these kind of scales of these costs and drilling wells and reviewing the data, they have a much higher risk appetite than most clients, which we found really good working with them. So yeah, we think hopefully, and we're pushing for the deployment of an exploration well and yeah, refining that and exploring those deep technologies. So quickly, I'll brush over this, but these are the kind of key opportunities and challenges. And as I recently mentioned, the largest risk to the project is that ground and hydrogeological uncertainty, and then the large capex required to de-risk these systems. So yeah, within that, you have the high productivity potential, which you have to weigh between the high risks. Further risks to the project can be the development timelines. So there's still a 2-year backlog for EA permits. And if you don't need the EA permits, it's still looking around a 3-year development timeline. And even for doublet developments, you're looking at total development timelines of 4 to 8 years. Luckily, yeah, the liquefied CO2 import phase is going to be the second phase of CO2 that they are pumping and storing at the Morecambe Net Zero project. The first phase is the Morecambe Net Zero to Peak Cluster pipeline, the CO2 pipeline coming from the Peak District. And then another thing that you have to consider with this is the scale considerations. So the large heating loads are greater than 50 megawatts that will potentially lead to the large scale installations and also the installation of multiple well doublets. And as I say, once you already have the drilling rig on site, you can then go through and produce multiple wells in one stint rather than having to pay for the equipment and the plant to be brought on and off site. So yeah, other options within the area. There are other industries within the Morecambe Bay and around the Barrow and Furnace port, such as bay systems, the gas terminal, some key other infrastructure, and these could be linked in with a local heat network and having cooling and heating to different off-takers. The key ways to refine this will be further drilling and testing, revising the capacity estimates, and also modelling the far field impacts on the CO2 reservoir. So if they're pumping significant amounts of fluid from the Sherwood Sandstone aquifer, which is connected, although 25 kilometres away, to the same hydrological system, that the CO2 is being stored in, that could impact, although unlikely. And yeah, as I'll mention on the next slide, next stages can also include economic modelling. So finally, what are the recommended next steps that we said? So we indicated and proved that the geothermal potential at the site is excellent. However, further evaluation is required to progress towards a viable project. They must review and shortlist the technologies. We put the deep geothermal as the best performing one, although the high risk is there. So we also suggested those de-risking options. So we'll suggest conducting the detailed whole life economic modelling, carbon assessments to understand the best solutions, and then increase that costing level of certainty to front end loading 2, which reduces it down to 25%. And then further de-risking through field investigations. The key thing here is drilling that first exploration well, where we can get hard empirical evidence of the target horizon and conduct the right downhole tests, including geophysics, and also then potentially doing a geophysical survey from above ground to model the environment subsurface. So that's the case study, and that technology pairing with geothermal and CCS can also be deployed in other locations, because as most of you are aware, and I'm sure all of you are aware, some technologies of geothermal can be deployed anywhere in the world. That's those closed loop systems. But with the kind of scales of heat demand that we require for CCS operations, the most likely option will be those deep wells or enhanced geothermal systems where you have hard rock. So let me just discuss about that. I'll quickly give a quick background to Arup's CCUS and CCS experience. So we've delivered projects all across the world involved in CCS infrastructure, from planning and consenting to engineering design, transport and storage, process engineering, mechanical, electrical, plant requirements. And so, yeah, it's something that we can deliver in-house and have those expertise and synergies between the two teams, where we work as one Arup and deliver that kind of technology pairing. So within the UK context, on the left, we have a figure of the current CCS projects across the UK. A lot of these are in clusters, and I'm sure you may have heard of some of the big ones, such as Acorn, the East Coast Cluster, and Viking. And then on the West Coast there, we've got Peak Cluster, which is where they're capturing the CO2, HyNet, which I mentioned earlier, where the overflow will go up to Morecambe Net Zero up in Barrow and Furness. So then on the right there, we have this great map from the recently published Project InnerSpace report, where we show the different sources of geothermal potential across the UK. So in the red there, you have exposed granites. In the dashed hatching, we have buried granites at depth. Then we have onshore coal fields in the pink, mineral mines with the little dot points, and then the thickness of sedimentary reservoir where you could target that open loop technology. So I didn't want to talk through all of them, as obviously there's a lot of projects here, but I thought I'd pick out some of the key clusters and where they really align with geothermal potential. So on the East Coast here, we can see there's that deep dark blue indicating a thick sedimentary reservoir at depth, and also some buried granites. And in that area as well, we have the East Coast Cluster in Teesside and Humber. And this is one of the most developed clusters that we have in the UK, and has been selected for the next stages of development through the Contracts of Difference. And with those two technologies, and also the fact that at this cluster, they will be importing CO2 from ships, where you will then again have that thermal energy challenge, where you have a large delta T. So this is one of the main areas where they could explore utilizing geothermal to enable the CCS heating pre-gasification, and while that storage is being brought in and processed at the site. Again, another one that could have great potential is the Viking cluster. Obviously, they're very close to each other, so they have both got a lot of potential for the same reasons. But another one that is a bit further away is down on the south coast, where you have that deep blue aquifer thickness and showing thick aquifer at depth. So really, this technology pairing is deployable in most locations. Fortunately, the geothermal and CCS hubs have been, well, the CCS hubs have been developed in areas where there appears to be a lot of geothermal potential. So this is one of those key offerings that we could look at, and technology pairings that can help decarbonize. And that's the key impact, really, that this kind of work can have. And the global first of a kind assessment integrating CCS and geothermal the technology requirements of liquefaction, lowering the operational costs and enhancing energy security, taking away the power demand from electricity, which is based on global gas prices. The both economics align with long life cycles, typically around 40 years. And while this technology pairing is at an early stage of development, hopefully a demonstrator could promote this and show that these synergies align. And finally, as CCS and geothermal are both growing global markets, they're key carbon reduction mechanisms and can support net zero. This is really important work that I've really enjoyed doing and feel passionately about. So yeah, apologies for running over by a couple minutes, but if there's any questions, please let me know. And also please reach out to me or through my contact details on the slide there if you would like to follow up. Thank you.
Thank you so much, Trystan. That was such an in-depth and insightful presentation. Yeah, we've got a few claps in the audience. Yeah, so the floor is open to questions now. The participants can see that your mics, you can now unmute yourself or turn on your cameras if you wish, which I do encourage people to do. If there are any immediate questions from the audience now, please just unmute yourself. Otherwise, I see some questions in the Q&A. Oh, okay. So yeah, we've got one hand up. Go for it.
Hello.
Hello.
My name is Çağan Çakıcı from Turkey. I am the mechanical engineer and power plant manager in Turkey. We have also same project in Turkey, CO2 injection to the reinjection wells, and we ordered the compressor and suspends the CO2 into the geothermal water and inject and compress the CO2 and inject to the injection wells. So the actual question is, actually, I'm curious about what was the injection pressure in your project? What was the well pressure?
The well pressure at the base of the reservoir is not something we looked at in detail in this study. So because this was an early conceptual study, we haven't looked specifically at the injection pressure, but in our geotechnical inputs in the modeling, you can look at the depth of that injection well at 1,200 meters. And if you take the traditional lithostatic gradient and the hydrostatic gradients combined, you could calculate that as something. Yeah, find that data out, but that's not something we looked at. And yeah, it's interesting that you talk about using the CO2 fluid, well, the geothermal fluid to enhance the CO2 storage and kind of bring those two technologies together in another way, not just utilizing that thermal energy. I have heard about that as a new advancing technology pairing. And yeah, if we could even store some of the CO2 in our geothermal wells, that is something you could look at, but then you'd also have to really consider what the containment structure is. So the key part of the CO2 storage reservoir is that it has that porous sandstone that the gas can be saturated within, but also a really essential part is that it has a clear trapping mechanism to keep that CO2 stored underground and let it react away into the mineral systems. So apologies, I don't have a direct answer for you right now, but if you want to send me an email, I can follow up and look into that with my team.
Okay, thank you. I will send an email later.
Yes, perfect. Thank you.
Yeah, excellent. Thanks for the question. Do we have any more questions from the audience? Okay, well, actually, I had one question, and I'll take the opportunity now. So, you mentioned that you actually looked at offshore wells that could have been geothermal wells. I'm just interested in how that assessment is different from drilling onshore geothermal wells, did you kind of assess that in the sort of like final, you have your risk, there was this table with like this graph with risks, etc.
So we didn't assess for installation of offshore geothermal wells to produce heat. We used the offshore wells for inputting into our ground model. So yeah.
Okay. Okay, well, there you go. There's
Right,
another
yeah.
idea.
So that's important to clarify that. But yeah. So yeah, I think, I don't know, could you use offshore submerged wells for geothermal? I guess so. I don't see why you wouldn't. They use it for oil and gas production, where they circulate and withdraw, well, where they withdraw fluids from the subsurface in the form of gas. But I guess one of the main limiting factors there would be the cost of installation, where it is much cheaper to install on ground and on land wells rather than offshore wells. And the payback there, unless you're generating extreme temperatures, probably isn't viable. And I guess also the other thing, because it's offshore, you're going to have to lose that thermally charged fluid. There'll be degradation of that during the transport process. But maybe
that's what I was thinking about, is how, you know, the surrounding infrastructure in transporting geothermal or geothermally warmed waters. But yeah, no, definitely a new idea added. Right, I think there's a question in the chat as well. So from Asad Ali. I have a question regarding CCS. What are the core challenges that companies face in order to deploy effectively?
So I think, yeah, thank you for the question, Asad. It's a really important question because, as we know, there are these net zero targets and the idea of net zero by 2050. And realistically, to deploy CCS, it needs to be for those hard to abate sectors, which is the bottom 20% of carbon reduction requirements. Ideally, we would be electrifying and finding alternative technologies before deploying CCS, due to mainly the main barrier being the cost and business model there. So with CCS, there is no value in storing CCS. There's no end product that you can sell apart from the fact that you're removing CCS from the atmosphere. So until the price of carbon, so it's all governed by the global carbon markets and the carbon trading mechanism and the price of carbon. So until there are policies and frameworks in place, so the UK used to have this policy called the Carbon Border Adjustment Mechanism, which regulated and forced the price of carbon to be valued at a higher level. Since we left the European Union, we no longer have that, and they're in the process of implementing a new policy. But yeah, at the end of the day, until the projects are economical and can self-sustain themselves on their own business model, which is all governed by the cost of carbon, then the projects won't be viable, because unfortunately money talks. So that's from the economic side. From a technical perspective, there aren't that many barriers, especially in the UK, due to our extensive experience within the oil and gas sector. So we have a lot of pipelines, we can reuse the well and legacy data. We have a lot of companies that are ready to transfer and upskill in carbon capture and storage. And then from a technical perspective, if you're talking on the reservoir scale, you're looking at the simulation of the reservoir itself. What kind of mechanisms of flow are you? What pressures are you injecting at? What temperatures are you injecting the fluid at? Are you going to have runaway effects such as viscous fingering, where it spills out of your trapping mechanism? And then also the monitoring, measurement and verification, which is a really big part of UK regulation and the awarding of a carbon storage license. The regulation of that modeling is the seismic data that you need before you can actually inject. You have to have a really comprehensive model of how that CO2 will behave in the subsurface. and that's very costly. And then that brings me back to the first point, which is who's going to pay for it and where's the money coming from to continuously monitor these systems and make sure the CO2 isn't escaping and that what you say is getting stored underground is actually getting stored underground. So yeah, there's covered a few things, but if you want a conversation about that outside of this, feel free to send me an email.
All right, we've received a thank you for the detailed answer. Thank you, Trystan, so much. So it looks like it is 1:30, and that will be essentially that's the end of our time here. Huge thank you again for Trystan to giving such an amazing talk in less than perfect conditions. I hope the AC unit has held up where you are.
Doing its job.
Good. But yeah, so I'd like to thank Trystan again, and thank you for everyone to attending this Wednesday with Wing webinar for June. And our next one will be in September. We're taking a break for the summer. So thank you all.
Thanks all.
Just